Let's study now graph neural networks. So let's start defining what is a graph. So a graph is these kind of structures where you have nodes, you have edges between the nodes, and it can be directed. We will study directed graph. So our graph will be directed, and we have this kind of way to describe the edges. So we will have all the nodes as rows and columns, and we will define the adjacency matrix as one that makes, for instance, if W is connected to Y, so W is connected to Y, so this is from 2. Okay, so Y is not connected to W, so Y to W is 0, but W to Y is 1. And so here you can put the adjacency is just who is connected with whom, but you can also qualify these edges, and you can put some numbers depending on, for instance, what is the strength of the connection, or what is the cost of going from one to the other, or whatever. They can also, given the adjacency matrix, we can define the degree matrix. The degree matrix, if it is an adjacency 0, 1, it is just how many connections each one of the nodes has. So it is a diagonal matrix where the elements in the diagonal are defined by this, and then that is graph in general, very simple introduction to graphs. So now what is regarding the neural networks, we will assume that each one of the nodes has a set of features, a set of labels, and a hidden state that will be called the node embedding. So we have two nodes here, the I and J. So Xi, so I has its own features and labels. J also has its own features and labels. And let's say that the adjacency matrix is like this. So J will collect information from the nearby neighbors, so from the nodes that are connected to them. So in this kind of networks, of graph neural networks, the one that we will explain are called message passing. So in the message passing, the node V receives messages from the connected nodes. So and the message, so the message is here. So the message, so V, say U is in the neighborhood of V. So the neighborhood is the nodes that are connected to V. So the message that it receives depends on the hidden state of V, the hidden state of U in those layers, so at the layer L, and the edge between U and V. So the edge is this element from the adjacency matrix. So V receives a lot of messages, then it aggregates all these messages into a single message. So that is the message for V at the layer L, and then it will update the message. So there is an update function that takes the hidden message, the hidden state, the message, and then produces the hidden state for the next one. And so here the layers are somehow represented by these three processes: message passing, message formation, aggregation and retrieval of all the messages, and then updating the hidden state. So here it has a different notation, but the concept is the same. So you have some input vectors. These input vectors are embedded into some state, and then these states, so this is the hidden state. So the first one, typically you start by just the input vectors, so there is no function here, but you can put a function also if you want. Then you construct the message passing, so you construct the messages, and then you collect all the messages here, you update your function. So you have some three important functions, and those are the ones that you learn. So the node embedding, the message forming function, and the update function. So graph convolution is a particular case of this message passing. So you start, as I said, without any input function, so embedding function, but you can put an embedding function if you want. Then you let them evolve. So the evolution is defined in this way. So there is a bias, the hidden state, the hidden state for the neuron J. J is one of the neighborhoods, is one of the neighbors of VI, and then the weight between the edge between I and J, and this is at time t. And yeah, this is layer 0, this is layer L+1, and then this layer L+1 can also be defined this way. So these are layers, not time. So these are layers. So this update can also be computed in this way, where there is an adjacency matrix that is transformed by adding the self connections. This is the degree matrix of this one, and so on. So here we clearly see the structure, the typical structure of the neural network. So it is the nonlinear function of something that depends on some connectivity function and some weights that you want to learn, and some bias. So the bias somehow goes into the W here, and the adjacency matrix that is extended. So that is why. Then another very typical operation is pooling. So how do we do pooling? So from one layer to the next. So there are multiple ways. One way is to do kind of node-wise local max pooling. So a node aggregates information from the neighbors by taking the element-wise maximum. Okay, so here are the neighbors in the previous layer. So we take the neighbors in the previous layer, we combine them with some weighted matrix, and then we take the maximum and we go through a nonlinear function. We can also compute a max pooling at the level of graph. So if we take all the nodes in the graph, we can produce we can take the maximum, for instance, of all the hidden states. The same applies to average pooling. And another way of doing graph pooling is the following. So we have kind of subgraphs. So this is the original graph. So we have kind of subgraphs, and these subgraphs are somehow represented here, and this subgraph is represented there, this subgraph is represented there. So we have a simpler graph. This simpler graph is further simplified in the next layer, and then another layer of pooling, and then this one will have a vector that goes to a feed-forward network. So, for instance, we can do this to do this kind of representations. We can do this differential pooling. So differential pooling, we have the node states in the previous layer. We go through some neural network, and this neural network will produce some node embedding, and then the node embedding set will be used in this way for the for the for the next layer. So it will be uh, multiplied by the matrix S, and the adjacency matrix will also be given by S. So S is the matrix that that clusters these subnetworks into simpler representation, and they are fixed. They could also be learned, so you can also put something to learn S. And top K is selects the top K nodes based on a learning score. So you multiply, so you are learning S, so you have the hidden states, you multiply by some weight vector that has to be learned, and then you are taking the top K with of all the scores. So you take all the scores and take the K that are better. So somehow this is also reducing the complexity of the input vector of the input graph to a simpler graph with different states. So typical architecture of graph neural networks. You start from a graph. The graph defines an adjacency matrix like this one, and then you do graph convolution, then pooling, graph convolution, then you put everything as a vector, and then you go for a multi-layer perceptron that will classify. So there are some graph layers here, and at the end you put a dense layer or several dense layers. Here we have an example at the level of code. So we will work with this Cora dataset, that is the citation network of almost 3,000 papers that are citing each other. Each publication is described by a binary vector of 1,500 words in the dictionary, and each one of them is classified into one of 7 classes. So all these are papers related to machine learning. So there are some of them related to the theory of machine learning, or rule learning, reinforcement learning, probabilistic methods, and so on. So we load the dataset, and then we define the graph convolutional network. So the graph convolutional network will have 2 convolutional layers. So we take the adjacency matrix and the node features. So the node features are this description in terms of words, and the adjacency matrix is the which paper is citing which paper. So we take the words and we convolve them using the convolution A. So the convolution 1 that considers the adjacency matrix A. So the adjacency matrix, as we saw, what we'll do is so we will initialize with the words, and then the next layer will be which papers, which nodes are updated with the messages from which other papers. So yeah, and then some nonlinear function, dropout, second layer of convolution, and then softmax. And then we instantiate the model, we take the optimizer, and then this is just training and test, how to do the training, how to do the test. So it is just steps of training, and this training is computing the loss and back propagating the error. and then we can show what is the final accuracy. So it classifies with 80% of accuracy. I think here we have the confusion matrix. So many papers, so the papers coming from neural networks are sometimes confused with some other papers, and also these papers based on case-based reasoning, they are sometimes confused with some other kind of papers. Here you have this example, and here you have another example if you want to learn how to do that for your graphs. That's all.